Hello everyone, welcome to the Physics Mage. This is a problem to build your understanding on how charges will interact in magnetic fields and also to learn how to mathematize a given logic. So let's try and solve. In this problem, we have a hollow rigid cylinder of radius r where gravity is absent here and uniform magnetic field of induction B is established everywhere parallel to the axis of the cylinder. So here already the direction of the magnetic field is given. It is out of the screen. The cylinder is made of an insulating material and is fixed by some external means, meaning if the charge interacts with the surface, there is no loss of charge, right? A very small ball of mass m and charge q is projected normally from a point P on the inner surface of the cylinder. If the ball returns to the point P after a certain number of elastic collisions with the cylinder, find the range of velocity v of a projection of the ball. This is the story. Now, what are the basics one should know? See, we have this magnetic field outside the screen, let's say. Suppose if you take a charge particle and if you throw in this uniform magnetic field, what will happen? So we'll be taking a charge particle q whose mass is m. If you throw like this with a velocity v and magnetic field is outwards, then v cross b, you know that magnetic force is given by q times of v cross b on a charged particle. This is Lorentz magnetic force. I hope you're all familiar with this. Now this one will experience Lorentz force exactly downwards like this. So as a consequence, it will describe a circular trajectory. And I hope you're all familiar with these basic ideas. The radius of this particular trajectory is given by mv by qb, where m is mass of the charged particle, v is the speed with which you are projecting, q is charge, and b is the magnetic field at that place. Okay, so we are using this one, and also we should know like time period of revolution will be 2 pi m by qb, or simply just can write it as 2 pi by omega. And also I would expect you should know the velocity with which it hits the platform, the same velocity with which it will be going back. If it is an elastic collision, the angle of incidence will be equal to angle of reflection. So these are few basics I would expect you to know. Now let's try and solve this problem. So we have this charge particle. Let me write this for my reference. If I take, these are the two perpendicular lines. Okay, so from this point P, we are going to project the charge particle. As we project the charge particle here, depending upon its velocity and depending upon its velocity, its radius will be decided as we know here from this one. Okay, r is equal to mv by qb, right? So they have already given this radius is r. So we'll be using radius of trajectory as r dash. Okay, now here as we projected, I'm just guessing like this charge particle will go travel like this and it might hit somewhere. Okay, so if this is a story, then it will hit here, this point, wherever it is hitting, right? That point I'm naming it as say q. Okay, we know that everywhere the magnetic field is outwards. So mv by qb is the radius r dash. So we can expect the Lorentz force will be acting exactly perpendicular to velocity vector. So here velocity vector will be exactly like this. So I'm just taking two lines which is making 90 degrees with this velocity vectors. Here it is just a velocity vector like this and q, and you know that speed remains same, it will only change the direction. Now for reference, we know that this is r dash, and from the center, if I name it as o, from this point to this point, let me connect with a line such that I'll be naming this particular position, right, as some theta. If this is theta, from here to this point, if this is radius r, even this one is radius r, I'll be constructing from this point to this point, there is one more line. if I consider one more line like that, if this angle is theta, then the other angle here, we can write it as 90 minus theta because we are considering this as 90 degrees and 90 degrees. So 90 minus theta, and this angle turns out to be theta. Similarly, this becomes theta then. So this overall angle becomes 180 minus 2 theta, right? Now, if we consider all these ideas, suppose if I name this one as O dash, right? So P O dash, that is R dash cos theta, right? R dash cos theta, which is equal to R times of sine theta, just from geometry, okay? So R dash is nothing but mv by qb cos theta is equal to R times of sine theta. Anyhow, we are interested in this v, so v can be written as qbr by m times of tan theta. So this is our expression, okay? Now, anyhow, we got this particular expression, v is equal to qbr tan theta by m. So in order to mathematize this idea of reaching back to the same point, we know that this particular charge particle should reach back to the point P, and this can happen like say having say first bounce, second bounce, and back to it after two bounces, or it can have three bounces coming back, or four or five, like that. It could be anything. So we have to mathematize this idea. So observe, as it is covering this 180 minus 2 theta, it is indirectly here covering 2 theta amount of angle, right? So we should be aware this 2 theta, some integral multiple. Let me use some m as a number. So m is for mass. So let me use some a or something. A times 2 theta should be equal to 2 pi. Suppose if it is a times of 2 theta is equal to 2 pi, what does that even mean? It means after a number of times, a times of 2 theta, so it comes back to the same point P, then it means that after going once around the center, like this, like say after suffering many collisions, if it is coming back to the same point P, after once around the center, it describes an angle 2 pi. So A is just some finite number. Okay. Now we can also have this kind of logic, right? So what if it misses the first time? What if it misses the first time? Like say somewhere it misses here, then again it might reach here in the second time. So then it is going to be a times of 2 theta should be equal to 2 times of 2 pi, right? Suppose if it is reaching there like the third time, third revolution, third time going around the center, okay, then it is going to be 3 pi. So in order to make it more general, it is going to be some b times of 2 pi. So we know that here a cannot be 0 and b cannot be 0. So I'm just generalizing this. I'll be erasing this. This is not required now. So this is what we have. So we can cancel 2 and 2, and theta can be written as b times of pi by a. So we'll be putting this value in our previous observation. So our answer turns out to be b equals qbr by m tan of wherever theta we have there, it is p b pi by a. So meaning it's not some range, there are multiple possibilities. Wherever this particular equation is valid, there we can expect the charge particle to come back to the same point P. So everybody, here B and A should not be equal to 0, and B obviously cannot be less than 1. Okay, so A by B, right, that we have to choose accordingly so that there are multiple possibilities. So if you have any further doubts, please post that in the comment section. Thank you.